Warning: chlorates and perchlorates are strong oxidizers and may burn dangerously when mixed with reducing agents. Ammonium perchlorate may decompose violently when heated. Wear gloves when handling them and place them away from heat sources. Hi guys, here is MIH. Since my series on making perchlorates through the thermal decomposition process, I've seen many people suggest me to try the electrolytic method, claiming it is much cheaper and simpler. I have tried the electrolysis multiple times but didn't succeed until recently, when I obtained a piece of titanium substrate lead dioxide electrode from another amateur chemist. It is obviously possible to make good lead dioxide electrodes myself, but I didn't choose to do that due to the toxicity of lead salts and the complexity of the procedure. In short, an antimony tin oxide layer needs to be coated onto titanium mesh substrate before depositing alpha lead dioxide in an alkaline bath and finally beta lead dioxide in an acidic bath. I might do it in the future, but for now I simply use an electrode made by someone else. Now, before we actually start the electrolysis, I'm going to give a brief overview of the electrolytic method for producing perchlorate. The anodic oxidation of chloride ions first produces the unstable hypochlorite, then chlorate, and finally perchlorate. While both sodium and potassium chloride is used in a chlorate cell, only sodium chloride is used in a perchlorate cell, as potassium chlorate electrolysis has very low efficiency due to its low solubility. Other chlorides like calcium chloride and barium chloride can be used, but their efficiency is also generally low due to the low solubility of the corresponding hydroxides. Of course, ammonium chloride can never be used, as explosive nitrogen trichloride would form. Ammonium perchlorate is instead produced by the metathesis reaction between sodium perchlorate and ammonium salts, which is what I'll be doing in this video. Ammonium chlorate is dangerously explosive, and it shouldn't be isolated in solid form. Thus, the presence of ammonium chlorate in ammonium perchlorate is very dangerous if the perchlorate is used in pyrotechnic and related applications. This video presents a convenient way to detect chlorate level in a perchlorate cell, allowing the ammonium perchlorate produced to be very pure and free from chlorate. Next, we discuss cell operation, and more importantly, choice of anode. The normal cell conditions of a perchlorate cell are relatively low temperature of 30 to 40 degrees C, a pH around 67, a high anode current density, and a concentrated electrolyte. The cathode can be virtually any common metal, but titanium works best as it is resistant to salt mist corrosion, unlike steel and copper. The choice of anode is a much more important issue. As we may be familiar with, producing chlorate from chloride can be done using simple anodes such as graphite or titanium substrate mixed metal oxide electrode, but they cannot produce any perchlorate, perhaps because of their low oxygen evolution over potential that oxidizes water to oxygen instead of chlorate to perchlorate. Instead, we must use an anode material having high oxygen evolution over potential, as well as electrolyzing with high anode current density to promote chlorate oxidation instead of water oxidation. Titanium substrate lead dioxide, pure platinum, and boron-doped diamond anodes can oxidize chlorate to perchlorate. Lead dioxide layers formed by the oxidation of lead metal does not adhere to the metal surface and cannot be used, and titanium substrate platinum electrodes are not recommended as they may corrode. Because of the high cost of pure platinum and even higher cost of boron-doped diamond electrodes, and consequently their smaller surface area lengthening electrolysis time, titanium substrate lead dioxide is used by nearly all amateurs. There is a long-lasting saying of lead dioxide and platinum anodes being corroded in chloride electrolytes and can only be used to electrolyze pure chlorate into perchlorate. In fact, both anodes do corrode slightly in a chloride electrolyte, but the corrosion rate only becomes noticeable if current density is excessively high, at around 0.8 to 1 amp per square centimeter. The corrosion of pure platinum and lead dioxide electrodes at normal cell conditions are negligible, while titanium substrate platinum may be corroded as the platinum layer is very thin. Thus, with a well-made lead dioxide electrode, it is not only possible but tremendously convenient to produce perchlorate directly from chloride instead of isolating the chlorate intermediate. Now let's start running the perchlorate cell. I weighted out 100 grams of sodium chloride and dissolved it in around 300 ml of water. I then placed a lead dioxide electrode and 2 titanium ore cathodes into the solution and begin electrolyzing at 5 amps constant current. The current is small at start, but rises to 5 amps in about 30 minutes as the electrolyte heats up. I used such a large beaker to decrease the anode area and increase current density. The 30 square centimeter of electrode area would give me a current density of 0.167 amps per square centimeter, which is decently high for the first stage electrolysis from chloride to chlorate. At 5 amps, it would take me around 6 days and 2 hours to convert all chloride to perchlorate, but the real runtime of the cell was close to 9 days, which I'll explain why later. The electrolyte was brown due to lead dioxide particles, as I accidentally connected the negative to the lead dioxide electrode. Lead dioxide electrodes can only be used as the anode, never the cathode, or else the lead dioxide layer will flake off due to reduction. I kept the electrodes in place using a piece of transparent plastic serving as a cover, but the evaporation rate of this cell is still really fast, and I need to add water twice a day to keep the liquid level. After a few days of electrolysis requiring a lot of attention and repair in between, I decided to construct a better cell. It is based on my previous chlorate cell and has a very similar structure. Basically, the cell body is a 1 liter borosilicate reagent bottle, and the anode and 2 cathodes are fixed through holes in the bottle cap. The anode is roughly sealed to the cap by some Teflon tape, and the 2 cathodes are surrounded by plastic tubes cut from pipettes and are connected by a stainless steel piece. The plastic tubes achieve a decent seal on their own and doesn't require any more tape. 2 small plastic caps with small holes, also made of pipettes, are placed above the tubes to prevent soap mist from being released. This design minimizes corrosion caused by the well-known problem of soap creep with minimal seals, enabling the cell to run without repair for a week or longer. Of course, many prefer to make the cell completely airtight with silicone, epoxy, or hot glue like in my previous cell, but I found that these reasons deteriorate after long-time contact with the corrosive electrolyte and chlorine ozone gases, so I avoided them. After around 6 days in, which was the theoretical time required for all chloride to convert to perchlorate, I decided to check the progress of the cell by carrying out tests for 3 ions, chloride, chlorate, and perchlorate respectively. The chloride test was done by a dilute silver nitrate solution, with cell electrolyte on the left and tap water control on the right. As you can see, no chloride is left in the cell, which was awesome. I didn't expect the conversion to be so complete. I choose to do the chlorate test with something called aniline reagent, which I'm making here, although other reagents such as phenamic acid can also be used. Aniline reagent turns blue slowly in the presence of small amounts of chlorate, rapidly in medium amounts, and to a red color in large amounts. The detection limit of this reagent appears to be around 1 gram chlorate per liter, as I show later. To 5 ml of 20% hydrochloric acid, I added 0.2 grams of aniline. The aniline produced fumes in contact with hydrogen chloride released from the acid and dissolved quickly to produce a clear, light yellow solution. I then added around 2 milliliters of the solution to a sample of cell electrolyte. It is clearly seen that the mixture turned to a distinct blue, which then darkened to almost black. This is a positive test for medium amounts of chlorate, as aniline is oxidized by chlorate in acidic conditions to produce polymers, perhaps aniline black that was showcased in one of previous videos. The perchlorate test is done using a dilute solution of methylene blue. This is a commonly known test among amateur chemists, and the formation of a purple precipitate, which was some kind of alum pair that agglomerates, indicates the presence of perchlorate. Despite finding many literatures on the detection of perchlorate by methylene blue, I didn't find much detail about the identity of this purple precipitate. And as you can see, the test is positive for perchlorate. The results from these 3 tests tell me that the conversion from chloride to chlorate is complete, but more time is needed to convert chlorate to perchlorate. I then allowed the cell to run for more time and continued doing the chlorate test using aniline reagent. This was a test after a total of 8 days of electrolysis, and nearly no color is seen upon adding the aniline reagent to electrolyte. As a control, a solution of around 20% sodium chlorate immediately turned red and then black. After 5 minutes, a blue color developed in the electrolyte, and another control was done using a 1 gram per liter potassium chlorate solution, where a tiny tint of blue is produced. 2 hours later, both turned to a similar blue color, showing that the amount of chlorate in my electrolyte is close to 1 gram per liter. The test after 9 days shows only a very light blue after 2 hours, so I decided to stop the electrolysis as chlorate level has decreased to negligible levels. Before proceeding to harvesting ammonium perchlorate though, I think it's worth to explain why I took so much more time than the theoretical and discuss optimizations that can be done on my cell. For example, chlorate cells are run at high temperature of 70 to 80 degrees C, but perchlorate cells are usually run at a much lower 30 to 40 degrees C to reduce possible electrode corrosion and increase current efficiency. Additionally, I used a rather small anode current density, and because of the large volume of my cell, I had to dilute my electrolyte quite a bit to match the level of the electrodes. Another thing I didn't mention is that current density drops considerably as chlorate levels fall, and nearly reaches 0 with the last trace of chlorates. Hence, in industrial plants, electrolysis is stopped when there's still 100 grams per liter of chlorate left in solution, and ammonium perchlorate is separated by fractional crystallization. But since fractional crystallization is very hard to do with amateur equipment, and I didn't like to risk contaminating my ammonium perchlorate with chlorate, I decided to go all the way and face the bad current efficiency at the final stages. Now we can finally move on to our last step, the salt metathesis reaction. I also want to thank the people who stayed with me so far in this very long video, and I really appreciate it. For this, I added 100 grams of ammonium chloride, or roughly 10% more than the stoichiometric amount, to the electrolyte. The ammonium chloride quickly dissolves, and the solution is boiled to concentrate down. By the way, the pH at this stage should be neutral or slightly acidic, and can be adjusted with a little bit of hydrochloric acid if it is not. Other ammonium salts, most notably ammonium nitrate, can be used to obtain a higher yield of ammonium perchlorate, but ammonium nitrate is very hard to obtain for me, and as we're about to see, the yield and purity of ammonium perchlorate using the present procedure is nice enough for many purposes. As the liquid volume reduces to around 500 mL, a thin crystal membrane appears on top of it, showing that ammonium perchlorate is saturated now and begins to separate out. The beaker is taken off heat and allowed to cool. This separation takes advantage of the nearly stationary solubility of sodium chloride in water, whereas the solubility of ammonium perchlorate changes much more significantly. The product may be contaminated by a few % of sodium and chloride, but for my purposes it is inconsequential. The contamination may be removed by more water washings or by adding around 30 mL more water back to the beaker when the crystal membrane appears. As the beaker cools to room temperature, large amounts of beautiful needle-like crystals of ammonium perchlorate separate out, which may be a little hard to see here. The mixture is suction filtered and the ammonium perchlorate is sucked as dry as possible before being washed with 20 mL of water. Some people choose to put the mixture into the freezer to squeeze more yield, but I didn't bother as the yield increase is small and the product is less pure. Also, the perchlorate remained in the filter can be recycled anyways, either by treating with potassium chloride to precipitate them as potassium perchlorate, or boiled and filtered while hot to remove sodium chloride and used as the mother liquid in the next batch of ammonium perchlorate produced. The yield of slightly wet ammonium perchlorate is around 170 grams out of the theoretical 201 grams, representing an 85% yield and is roughly the same as the yield of other amateurs, around 80%. It is allowed to air dry by spreading on 2 printer papers with kitchen tissue paper placed underneath to remove remaining liquid. This ammonium perchlorate will be reused in future videos to revisit making perchloric acid and to make APCP rocket fuel. Thanks for watching and see you soon.